Hello everyone, welcome back to the NPTEL course on materials informatics, and today's lecture we will be discussing about some of the classical machine learning models that are commonly used. So let us get started. So just to give a brief recap of what we have done in this course so far. So we looked at a typical regression problem and workflows associated with the typical regression problem. And the problem of interest for us was predicting median house prices in the state of California. We also looked at a typical classification problem where we wanted to predict what a given handwritten digit was that were available in the MNIST database. And we also looked at some hands on exercises of regression problems involving materials related data sets and also classification problem involving materials related data. So in each of these regression and classification tasks the sort of workflow is similar. So the first thing is we have to obtain the data, and then we have to check the data itself. So visualize the data, compare it with different features, understand some amount of correlations with the data, and then we will have to prepare the data for machine learning. So that could be taking care of some missing data points, making sure that our data is scaled, so that could be either standardized or normalized, and then converting some of the text data or difficult to handle data into numerical forms. So we looked at several ways of preparing data for machine learning, and we did fit several models. So we looked at linear regression, we looked at decision tree, random forest, support vector machine, and in the case of classification we looked at KNN, so k nearest neighbors. We also looked at stochastic gradient descent classification and so on. So we have already looked at several different models. We also looked at how to optimize hyperparameters using either a grid search cross validation or a randomized search cross validation score. And we also tested our models. So in the classification task we did not really test the models very rigorously, but in the regression task we did examine how the models perform on a test set. So in this lecture and in the subsequent few lectures we will be looking at some of these classical models. So the sort of brief mathematical overview of how these classical machine learning models work, some of the key hyperparameters associated with these classical models, what algorithms are used typically to fit these models, and then any regularization schemes or steps that we take to ensure that the models are not overfit. These models that we are going to discuss are called classical models because they predate the development of, or at least they predate the use cases of neural networks. So neural networks were actually developed way back, at least the origins of the neural networks that we currently use, they were developed way back, but we will see in the course of the of the lectures in this course that the neural networks did not really pick up in terms of applications, but these classical models did. So these are mostly analytical models, so they are open box in some sense, so we can understand what really goes on in these models. So that is why these are called classical machine learning models. Just as a point to note, all the schematics that I will use in these in these slides are part of this textbook from Aurélien Giron. We will be covering from chapters 4 to 8 in this in this set of classical models, and unless otherwise mentioned assume that the schematics are from this textbook. Alright. So in this lecture what topics will we cover or in the subsequent few lectures. So we will cover a few models, so be it linear, polynomial, logistic models, support vector machines, some decision trees, k nearest neighbors, and ensemble methods. So we will increase the extent of complexity as we go down in this axis. We will also look at some dimensionality reduction algorithms that are available. And these dimensionality reduction algorithms sort of form the rough base for unsupervised learning as well. So all of these models are all supervised learning models. Dimensionality reduction we will look at simpler algorithms which will form the base for understanding how unsupervised learning generally works. in terms of algorithms, we look at gradient descent as a key sort of algorithm that is commonly used in several of these machine learning models. We will also look at some regularization options that we have, and the key hyperparameters associated with both the models and also algorithms and regularization options that we use, right. So each of these three things have hyperparameters associated with them. So whenever we introduce new algorithms or new regularization options or new models, we will understand what hyperparameters are associated with them. So in these set of lectures, we will be using code snippets instead of using actual notebooks. So once we introduce all of these models, we will then go through a hands on session, a tutorial session, where we actually compare and contrast the performance of different models. But for now, we will look at only code snippets to get an idea of how to, if you were to once again open a Jupyter notebook, how would you initialize these models and fit these models. So we will look at some code snippets where relevant. Okay, so let us start with the simplest machine learning model, which is our linear regression model. So why is it called linear regression? Basically it assumes that your target variable here, or target value here, y, is a linear function of all of your features. So here your x1 is a given feature, your x2 is a given feature, and so on, right. So if your y is, let us say, the median house price in California, your x1 could be your median income, your x2 could be your population, right, your x3 could be total number of rooms, and so on, right, your xn could be location, latitude, longitude, and so on, right. So we have several different features, and each of the features linearly correlate with our target value, our target metric. And it is obviously linear because the powers are associated with the individual features are all 1. So it is x1 to the power 1, x2 to the power 1, and so on, right. And each feature multiplies with a numerical factor called theta. So x1, for example, multiplies with theta 1 here, and this theta is what is referred to as weights, right. So individual features contribute to the overall target variable through its weight here, right. So the weights are higher, then the individual feature is contributing to a larger extent to the target value. If the weights are lower, then the individual feature is contributing to a lower extent, right. We also have a constant term theta naught here, and that is referred to as a bias term, right. So in any machine learning model, you will always have a set of bias terms and a set of weights. So in linear regression, you only have a single bias term and a collection of weights. So and the number of weights is equal to the number of features you have, right. But in as you increase the complexity of machine learning models, you will have multiple bias terms and multiple sets of weights, right. So whenever we are trying to fit quote unquote fit a machine learning model, we are trying to determine the values of these bias terms and these weight terms, right. So that is what we are trying to do. So instead of writing this in this big clunky mathematical form, we can use a compact shorthand form. So we can write our target variable as h of theta of x. So h theta is basically a collection of weights. So think of this as some kind of a mathematical function. So any given collection of weights gives rise to a distinct mathematical function, right. So if you change the value of theta 1 and theta 2 and substitute the same x values, right, you will get a different value of y, right. So you can call the collection of weights and biases as h of theta as a function, and that function operates on your input features, your x. So here x is a vector of features, right, that you have for each data point. So you can also denote this for linear regression as just theta dot x, right. So theta is let us say one vector and x is another vector, so it is just the dot product between the two vectors, right. So this theta dot x is a simplification for linear regression. H theta of x is a general notation that can be used for any machine learning model. So h of theta basically refers to a collection of your weights and biases and whatever mathematical functions or relations they have, right, and that function basically operates on your input features to give rise to your target, right. So linear regression as a model is very simple, right. It is mathematically the most intuitive of models. So it's very intuitive, very easy to understand, but it can have significant accuracy limitations, right, because to very trivially put it, right. So let us say you have your target variable varying as a square of x1, right. So let us say it has a parabolic dependence on your x1 feature, and if you try to fit a linear model to it, you won't get a good fit, right. So it can have significant accuracy limitations, especially when you have non-linear dependencies of your target with respect to your individual features, right. But if the data is largely linearly dependent, then this is a great model, right. So what do we do in our machine learning exercise? So we typically try to find our theta, so we try to find values of weights and biases that minimize some kind of a score, or minimize or maximize depending on what model we train. In the case of linear regression, we are minimizing our score, which is our mean squared error here, right. So how do we define mean squared error? So for any given set of features and weight terms, theta transpose times x, right, this is basically your dot product here, theta dot x, right. These are your set of predicted values for any given x, and y of I is basically your set of target values, right. So you take the difference and square them, and average over the total number of target points you have, total number of data points you have. So that's your typical definition of mean squared error. I just reintroduced this definition of mean squared error so that you are familiar with this notation of h of theta and x, right. So this is the same metric that we discussed in the previous lectures as well. So we try to identify theta that can minimize your mean squared error, right. Now the good thing about linear regression is that since the model is so simple, you can actually directly determine theta by minimizing mean squared error using what is referred to as a normal equation. Now we won't get to the details of this is a very straightforward result coming from simple linear algebra. So basically you can directly calculate theta that minimizes mean squared error with this mathematical operation here. So if you have a feature vector x, so you take the transpose of that feature, multiply that with the original vector itself, so you get a square matrix basically, and you can take the inverse of that square matrix, and then once again multiply that with the transpose of your original feature vector and your target vector here, right. So think of this as basically x transpose, so think of this as y by x roughly. So you have x transpose y in the numerator, and then this is the inverse of a matrix is roughly 1 by the matrix, so it's roughly the denominator. So you are roughly doing y by x, right. So you are saying that every value of theta corresponds to the target value divided by the corresponding feature value, right. That's roughly what you are doing here. So you can directly determine theta using this very simple mathematical operation. This comes from simple linear algebra here, right. But this process of minimizing of finding theta that minimizes your mean squared error can be computationally very expensive if you have a large number of features, right. So if your x vectors are very large, right, then this matrix multiplications and the inversion takes a lot of computing effort, right. So for smaller data sets this is okay, but for larger data sets or larger number of features that you have, in general this is not the best way of determining the ideal theta, right. But the good thing is you can directly determine theta as well. And if you want to use a code snippet example, so let us say you want to determine this by code, the way that you can do it is you can call a variable called theta best. So this basically gives you the best theta, and I am basically writing this whole mathematical operation as a code snippet here using NumPy arrays, right. So there is a very nice package called linear algebra within NumPy itself, right, and that has a lot of matrix operations built in. So INV stands for inverse, which is this operation here. So you are taking the inverse of x transpose, so dot t basically gives you the transpose of your original vector, so that is x dot t dot x, right. So that is this operation here, and then you have taken the inverse, and then you do dot of x dot t, so that is multiplying x dot t x transpose here, and then you multiply your target vector here, right. So this is a very simple way of identifying what is the best set of theta values, okay. So in practice, how do you do linear regression, right? So you typically don't invoke the normal equation. So you use implementations that are directly available in scikit-learn. This we have seen before also in our regression workflow. So from scikit-learn linear model, you import this linear regression class, right? You create an instance of the class and then you fit with our typical syntax fit of x comma y, and for any new data points, any new features, you just pass in the new features to the predict function and it should be able to give you whatever it is able to predict. And if you want to explicitly get the bias and weights, basically bias and weight parameters, the intercept basically gives you the bias, right. So you invoke the linear regression instance and then you call the intercept attribute within it, and then coefficients basically gives you, if I am not wrong, an array of the weight terms that contribute to your linear regression model. Now the default implementation within scikit-learn uses what is referred to as a pseudo inverse technique. So this is basically to invert fairly big matrices, right. Once again I will not get into the details of how this mathematically works, but this pseudo inverse technique basically scales as order of n square and order of m, where n is the number of features and m is the total number of data points you have. So for larger data sets, it sort of scales linearly with the number of data points you have and square with the number of features that you have. So if you have a large number of features, this algorithm will get very slow very quickly because it scales a square of your number of features. So for any models that has a large number of features available, we probably need a different algorithm. So what algorithm is commonly used in fitting of machine learning models? One of the most common algorithms is what is referred to as gradient descent, right. So this is a very generic optimization algorithm. There are several variants of it and is very commonly used, right. So basically to understand how gradient descent works, maybe you can try to answer this question, right. So how will you get down a mountain quickly, right. So you could say that the safest way to get down a mountain is to sort of loop around the mountain like a corkscrew, right. So go slowly in steps, right, and then that will bring you down to the mountain, but you may have to spend a lot of time walking around that mountain, right. But the fastest way to actually get down the mountain is to identify which is the steepest slope of the mountain and then walk along it, right. Now that may not be the safest way, you could get injured very quickly. I mean, imagine that you have a cliff, right. So if you have a cliff, the cliff has the steepest slope in a mountain. If you fall off the cliff, that's you basically reach the base of the cliff most easily, but you may injure yourself quite heavily, right. But we are dealing with algorithms here, so algorithms can get injured, so that's okay. So the swiftest way to get down a mountain is to estimate at any given instance or at any given point within the mountain where you are standing, to calculate what is the direction in which the mountain is sloping down the greatest, and then you walk along that direction, right. So you calculate the gradient along different directions. So let's say you are standing in this mountain, you calculate the gradients along different directions, the slopes as the mountain height is decreasing along different directions, and then you evaluate which of them has the greatest slope, right, the largest slope, and then you pick that direction, you walk along that slope, right. So that in essence is what happens in gradient descent. So you calculate the gradient, pick the maximum gradient, and then descend along that direction, right. So here our mountain is basically our mountain of errors, right. So we are standing on top of our error mountain and we are trying to minimize the errors here, right. So that is what we are trying to do here. So the way gradient descent works in practice is that it measures the slope of the error function. So this is our error mountains, right. So for each of the error mountains that we have, it measures the slope of these error mountains as you keep changing your theta, as you keep changing your weights, right. So if you were doing this in person in a real mountain, you would do it as a function of directions, right. In a mountain of error, the directions are all dependent on the weights and biases that you have, so they can vary as a function of theta, right. So you measure the slope or the gradient of your error mountain with respect to your theta, right, with respect to your weights and biases. You pick the maximum the direction of maximum decrease, right, or maximum slope, and then you propagate or you sort of update the values of theta along that maximum direction of error slope, right. So that is what happens in gradient descent. Okay. So typically gradient descent as an algorithm works very well when your cost function or your error function is convex in nature. Now what is a convex function? A very simple smooth bowl is an example of a convex function, right. So you have if you look at a parabolic bowl, for example, you have the outermost rims of the bowl being very smooth, so and they are monotonic, so they either, if you look from the bottom they monotonically increase, or if you look from the top they monotonically decrease, right. So if you take a cross sectional or a projected view of the height of the bowl, for example, right. So let us say the height is proportional to the amount of error that you are making, and this is the projected view of that height with respect to your features, right. So features could be directions in a bowl, right. So let us say you start from the tip of the bowl, right, all you have to do is gently roll down, right, roll down and you will reach the center of the bowl which has the lowest errors, right, or the lowest cost, right. So think of it as you initializing a ball at the top of a bowl. If you just let the ball roll down the bowl, it will find its minimum position or its what we refer to as an equilibrium position in classical mechanics towards the center of the bowl, right. So it will just find it there and stay there, right. And that sort of the reason why the ball does it is it tries to minimize its potential energy, right, in classical mechanics. Here we are trying to minimize our error, so we are starting from the edge of the ball which has maximum error, and then we are trying to get to the center of the ball which has the lowest error, right. So if you have error functions that are these kinds of convex functions, so very smooth functions, then gradient descent works excellently, right. But unfortunately most cost functions, most error functions in machine learning are not smooth convex functions, so they are not smooth bowls. You will come across instances where you have some kind of local minima, right. So let us say you have an error function that is varying non-monotonically like this, you may have instances where you hit a local minima, so this is a sort of a local solution for your weights, but it is not the most optimal solution. The most optimal solution is here, right. So if you start from here, right, your gradient descent can sort of go down your error function, but it may get stuck in this local minimum, right, and it may never be able to find find a global minimum, which is actually a better set of weights and biases that you should get for your model. The other scenarios, you can also run through large extents of plateaus, right. So if you think about a plateau, right, so if you are walking along a plateau and if you are trying to get down from a plateau has almost zero slope, right, in any of the directions, right. So that is the definition of a plateau, it does not vary in height, right, as you walk along either in x or y directions, right. Same thing in the case of error functions, right. So if you are calculating slopes and if the slopes are very small, then you may have to take a lot of steps, right, before the model can actually reach an optimal set of weights. So the model will basically be stuck here, right, in this plateau for a long period of time. So you will have to spend a lot of computing resources to slowly move your model from here to the global minimum, right. So if you have non-monotonic cost functions, gradient descent can get stuck, right. So it can turn into a fairly expensive algorithm, but as long as the cost function is smooth like a bowl, so if it is a convex function, then gradient descent works excellently, right. Now the good thing about linear regression is that if you look at the mean squared error as a cost function, so if you are trying to minimize the mean squared error, then this is a perfectly convex cost function, right. So you can sort of blindly use gradient descent in a linear regression model simply because mean squared error is a convex cost function and your gradient descent should work fairly well, right. So with gradient descent there are hyperparameters that we should choose as well, right, and one of the most important hyperparameters is what is referred to as learning rate or learning step here, right. So learning rate is typically defined with the symbol eta, so this is quite commonly used in all types of machine learning models. So if you see a hyperparameter named eta, understand that it corresponds to learning rate. So what is learning rate, right. So let us say you have this very smooth convex function here, you are starting from this point and then you are trying to get to the minimum, right. So you are starting here and then you calculate the slope and now you want to go down this curve, right. But you also have to decide how much you want to move along this curve, right, because if you take very small steps, right, like this, you may spend a lot of time, right, reaching from this initial point to your minimum, right. So that adds a lot of computational load, right. Now if you take very large steps, for example, so let us say you start here and you take a giant step, you may actually overshoot the minimum and go here instead, right. And same thing, if you start from here, maybe you overshoot the minimum again and then go here and so on. So you keep oscillating instead of actually identifying your local minimum. So whether your step is too small or whether your step is too large, you are almost always going to spend a lot of computational effort and time in trying to identify your minimum, right. So we have to take some kind of optimal steps, right, so that we arrive at the minimum with as few computations or computational efforts as possible, right. So the size of this step is what is determined by your learning rate, right. So this is a very important hyperparameter. So learning rate determines what steps you are going to take as you keep evaluating your gradients in your approach to your minimum value here, right. Learning rate is also associated with a couple of other things. So for example, if you have your models are normally learnt in a fairly iterative fashion. So what I mean by iteration is that, so let us say you start here, going from this step or this value of your weights and biases to this value is one step in the model or one step in its learning. We also call this as one iteration, right, of trying to learn the model. So this is iteration number 2, iteration number 3 and so on, right. So if you have m data points, right, in your model, so m is the total number of data points in your model, and if you complete m iterations, so let us say you have 100 data points and if you complete 100 iterations in trying to fit the model, that is typically referred to as an epoch, right. So normally when you sort of fit machine learning models, the number of epochs is something that you may have to specify when you fit the model, and this is one important hyperparameter, because if you are using too few epochs, maybe the model is not good enough. If you are using too many epochs, maybe the model has overfit. This is not strictly applicable to linear regression, but for models with higher complexity, if you use too few epochs, probably the model will underfit. If you use too many epochs, the model will probably overfit. So number of epochs is once again an important hyperparameter, and the number of epochs is tied to your learning rate as well, right. So if you have higher or lower learning rates, the optimal number of epochs will also change accordingly, right. In typical machine learning models, we typically define either set of epochs that we have to run or train our model on, or we stop training our model, or we stop the number of epochs as long as the sort of cost function or error function reaches a tolerance value of epsilon. So we either define the model to train for a certain number of epochs, or we say keep training until you reach this tolerance value, right. So this is another important hyperparameter that we must keep in mind, that is associated with learning rate. So for linear regression, learning rate is important, number of epochs is not very important, but as you increase complexity of your model, which we will, right, so the number of epochs plays a fairly important role there. Okay, so how does this learning rate vary in practice, right? So let us say your y is your target value here in all of these 3 plots, your x1 is your feature, right. Let us say this is if you the blue circles here are the actual data points, so your y is sort of varying roughly linearly with respect to x, right. So if you have a line that is passing through here roughly, right, then you have a reasonably good model, right, of y as a function of x1, right. So let us say this is your starting point here, your red line indicates what is the starting value of your weight associated with x1, so your theta 1 basically. So this is usually done randomly, so you randomly initialize the theta value and let us say that gives you this red line here. So of course you see that the red line is a very poor fit of the actual data points, right. So your model is trying to learn, or it is trying to fit with a very low learning rate. So 0.02 can be a very low learning rate for linear regression. So if you have low learning rates, your theta will also get updated very slowly. So even after you complete, let's say 10 steps, you are nowhere close to the optimal fit, right. So the optimal fit is somewhere here, the line should be here, but you are nowhere close to your data points, right. So even after about 10 iterations, you have not reached your optimal model, right. Let's say you use a very large learning rate, so let's say about 0.5, then you may start here, right. Your first iteration may actually go all the way here, right. So you have taken a very large step, right, whereby you have completely missed the data points, right. And maybe then after that you are trying to course correct, you predict a line here, right, which is again very wrong, and then you again try to course correct, you predict line here and so on. So you keep oscillating around the data points, the set of data points, but you never reach close to the optimal fit, right. So large learning rates bad, very small learning rates also equally bad. But if you use an optimal learning rate, let's say 0.1, you see that in about 10 iterations or 10 steps, right, you reach close to the optimal fit, right, which is the dark blue line here that is approaching or roughly cutting through the middle of the data points here, right. So it is very important in any machine learning model to always use the optimal learning rate. So learning rate is almost always one of the first hyperparameters that we will tune in a machine learning model. So one idea is to always try to change learning rate by a few orders of magnitude to find the optimal value. You will quickly see that if you are using too small learning rates, your model is nowhere close even after running for a few hundred epochs. If you are using too large learning rates, then you will see that the model diverges, it keeps oscillating, right. So you just have to vary it over a few orders of magnitude, and you will be able to immediately identify which is the correct learning rate. Okay. So with respect to gradient descent itself, there are different ways of calculating slopes, right. So as I said, gradient descent calculates the slope of your error or your cost function with respect to your theta values, your weights and biases, right. But does it calculate the slope considering all the data points in your data set, right. If it does that, so let's say you have 100 data points in your training set, and at any given step, right, your model actually calculates the slope of your error function with respect to your theta values, your weights and biases for all the 100 data points, right, and then it calculates some, let's say some kind of an average gradient, right, and so sort of identifies the maximum value or the direction with the maximum descent, right, from that calculation over 100 data points, all the 100 data points, then that is referred to as batch gradient descent, right. So here you calculate the slope of the error function with respect to your weights and biases across the entire data set, right, before determining the direction of maximum descent, right. This is a fairly robust way of doing gradient descent, but it can also be very expensive, especially when you have very large data sets that run into millions and billions of data points. Even in some cases, even hundreds of thousands of data points, batch gradient descent can be very slow, right. So you can also think of a completely extreme opposite of batch gradient descent, which can be what is referred to as stochastic gradient descent or SGD, right. So in stochastic gradient descent, you don't take all the data set to calculate the slopes, right. You just take one instance or one data point at random, you calculate the slopes, determine the maximum direction, and then you go down that direction, right. So that's why it's called stochastic. So stochastic means random, right. Now stochastic gradient descent can be quite cheap to calculate, so it can be computationally inexpensive, right. And it can also be used from to sort of perturb your model as it gets stuck in local minima, right. So we saw in one of the previous slides that gradient descent can actually get stuck in local minima quite abruptly instead of moving towards the global minimum, right. Whereas if you used stochastic gradient descent, the data point that you choose at random may be an outlier for that local minima, which could push your model away from the local minima towards the global minimum. But since it's stochastic, it's random, right. This also makes the gradient descent algorithm not converge as systematically as you would expect in batch gradient descent. So in batch gradient descent, your algorithm will converge in a fairly systematic fashion. In stochastic, there is no guarantee. So your algorithm can oscillate quite a bit even around the global minimum, right. Something in between batch and stochastic gradient descent is what is referred to as mini batch gradient descent. So this offers some kind of a balance, right, between calculating the slopes across the entire data set or calculating it for only one data point. So here you collect a small batch of your training data points. So let's say out of 100 data points, you calculate the slope for only 20 of those data points at any given step, at any given learning step, and then you use those calculations over those 20 data points to determine which is the direction of your steepest descent, right, and then you keep moving your model along that direction, right. So mini batch sort of offers a balance between batch, which can be very expensive to calculate, and stochastic, which can be cheap to calculate but can also cause some oscillations within your model. So mini batch is very commonly used in many of the modern machine learning algorithms. You can also use this image here to get a sense of how these different gradient descent types work, right. So if you have batch gradient descent, you see that it is systematically going down your error function. If you have stochastic, you see that it is oscillating quite a bit, right, as it goes down, and if you have batch, it probably oscillates a little bit, but it is able to systematically go down better than your stochastic, right. So this is how you can sort of visually interpret batch, stochastic and mini batch, right. And just as a recap, right, so we have already used this SGD classifier or stochastic gradient descent classifier in our classification exercise, right. So you can use either this SGD classifier class or SGD regressor class to do either batch or mini batch or stochastic. So there are keywords or parameters within these classes which lets you determine how you do your gradient descent, right. So with this we will stop today's lecture. So we did cover linear regression, we did cover a little bit of gradient descent, right, as an algorithm, and learning rate as a hyperparameter, and in the next lecture we will continue to look at other classical models. So we will start with polynomial regression, and we will look at other hyperparameters that come in. We will also look at some regularization options that we can exert to ensure that our models fit optimally, right. So with that, I thank all of you for joining today's lecture. I will see you all in the next one.